Marhaba. Okay, in this video we want to talk about statements in predicate logic which uses two quantifiers or more. Okay, so remember, just to recap, that we introduced what we mean by a predicate, say p of x. Okay, now what p of x is a shortcut for the statement the variable x has property p, and then we introduced how we can quantify these predicates either by applying the universal quantifier on this predicate. So here we have for all xp of x, or we can apply the existential quantifier on the predicate. And notice that this predicate, we call it a unary predicate because it talks about one variable only, and we also have on the side a domain of the variable x. Okay, and this domain has values from which we choose to substitute for x. And once we have the domain, then the first statement, the universal statement, the universal quantification, is we declared it to be true if every element in the domain has property p. So we go check that every element here in our domain, we have 5 elements. If each one of them has property p, then we say this is true. Otherwise, if one of them doesn't have the property p, say p is happy, p of x is happy, you look at these 5 people, if each one of them is happy, then for all xp of x is a true statement. If one of them is sad, then not everyone is happy, so for all xp of x is false. For the second one, there exists xp of x, means that there is at least one element in the domain, say this, or maybe 2 or 3, which are happy. If at least one of them, we just want one for the second statement, for the existential statement to be true. Okay, if no one is happy in our domain, then there exists xp of x is false. So you need to think about these statements, these as one statement. Okay, so this is one sentence which says there is somebody in the domain which has property p. Okay, now we want to study predicates, binary predicates. Okay, so for example, think of the predicate p of xy, which says that the pair xy has property p. Both of them together have property p. For example, p of xy could be x is the parent of y. Okay, so this is the property p, that the pair xy, they have property p if the first element in the pair is the parent of the second. Okay, so for example, suppose Dina is the parent of Khaled, then this then this will be a true proposition. Okay, now if Dina is not the parent of Huda, then say Dina and Huda don't have the property p, because Dina is not the parent of Huda, so this will be a false statement. Okay, now we want to study what will happen when we apply quantifiers to binary predicates. Okay, let's do it first step by step. So let p of xy be a binary predicate, whatever the property is. So this says that the pair xy have the property p. Now let's apply the predicate, the existential quantifier. So now what do we have? We have a new statement in predicate logic which says there exists y, so there is some element in the domain such that x with y has property p. they have property P, but not now. See here, now we call in this sentence we call y a bound variable because it is bounded by this quantifier, and x is a free variable because we don't have any value for x. For y, we know that there is some y in the domain, but x here you are free to do whatever you want with it, either substitute a value or apply a quantifier to it. So let's apply a quantifier to this statement, okay, the universal quantifier. So now we read this statement from left to right, okay, as we read English. Let me write down how do we read it. It says for every x in the domain, so for every element in the domain, we know that there is some y in the domain, there is some y, okay, such that p of xy is 2. Okay, now let me explain more the structure of this sentence. Okay, let's compare for all x and then the shaded sentence with this one. Okay, so what does this, like this one says every element in the domain has property P. Now in this one it says for every element in the domain it has this property, not property P, the new property, which says that every element in the domain has the property that you can find some element in the domain y such that xy has property P. Okay, so this is a more complicated property, but let's try to explain it. Suppose pxy, now suppose for an example that pxy says it's a predicate, which means it's a descriptive sentence which says x is the parent of y. Now what is the highlighted sentence? What does it say? So there exists y, p of xy. This is the property that every x has. So for all x, let me put it in also in red square, red rectangle. So we say that every element x in the domain has the property inside the red rectangle. So what is this property? It's this property. There exists y, p of xy. What does it say? That there is an element in the domain such that x is the parent of y. So it says there is y, okay, such that I will write it as s dot t dot, such that x is the parent. Okay, so this is parent and this is the child. Okay, so this is the property. So x has this property, which is in the red square, if you can find somebody in the domain. Say our domain is the set of people. So x has property which is inside the red rectangle if you can find some person in the domain in which x is the parent of it, or in other words, such that if you can find a parent who's the son of x. So what does this mean? Let's read it in when the domain is the set of people, and when pxy is x is the parent of y. It says for any person, for any x in the domain, which means for any person. Okay, what does it say? For any person, this property is true. There is somebody who is the son of this person. So this means for any person, there is someone who is their child. Okay, this is a long sentence. We can say this in short: any person has a child. Okay. So has a child is this property. It is the property in the yellow, the highlighted property. So there exists y such that y is the son or the daughter of x is the property, and we are saying we are saying that every element in the domain has this property. Okay, I hope now it's clear. Now let's swap the quantifiers and see that the meaning changes of the sentence. Let's say there exists an x such that for all y, p of x y. So what is the meaning here? How do we again we read it from left to right, and what do we say? Here is the domain of our people. Let's use the same domain. So this says there is an x in the domain. Okay, let me put it in a big red dot. There is some element x, so this is the element x with this property. And what is this property? Let me highlight it. So this sentence says that some element in our domain has maybe more, but there exists x says there is at least one. So there is at least one with this property. And what is this property? It says that for all y, x is the parent of y. So, which means for any person in our domain, for any person, x is their parent. Okay, so this means that x is the parent of this person, and x is the parent of this, and x is the parent of this, and also x is the parent of itself. This is what it says. Okay, so in English, this says there is someone who is the parent of everybody, right? There is someone such that for anyone you choose, you will find that x is the parent of y, which means x is the parent of everybody. There is someone who is the parent of everyone. Of course, this statement is false in our world, because in this current world, there is no person who is the father or the mother of everybody. Okay, I hope so. Just to compare it with the unary predicates, so now before we said every element x has property p, and now or there is an element x with property p. This is in the case of unary predicates. Now we have binary predicates, and this one says for any element x we have this property, but this property in the red rectangle includes another quantifier. Okay, so the property here, it's a little bit more complicated than just being p. It says that there is somebody who is the child of x, and this says there is somebody in the domain who is the parent of everybody. So there is somebody x such that if you choose anyone in the domain, you will find out that x is the parent of y. Okay. Now let's take more examples. Okay, look at this example. Let's say in the world of positive integers. So positive. Suppose our domain is positive integers, and by this I mean the set start 1, 2, 3, 4, all whole numbers starting from 1 and so on. Okay. Now we will talk about the binary predicate x is strictly less than y. So see, this is a predicate. It's a descriptive statement which says that the variable x is less than the variable y. Okay, we will apply two quantifiers to it. First, there exists y, and then this is a new statement in predicate logic. We will apply the universal quantifier to it. So now we get this statement. So this is Example 1. Let's see what can you write this in English? We want to write this in English. So what does it say? For every x in the domain, but what is our domain? It is the positive integer. So this means for any positive integer x, there is some so this says for any positive integer x, so x is somewhere here in the positive integers. So choose any x in the integers. You can find, so there is some positive integer y such that x is less than y. So you can find some integer y in which x is less than y. So y must be, so here say 100, 101, I don't know, you can choose y to be 101, say x, we chose 50, and now you can find the y, say 101, which is bigger than 50. Okay, so this is what it says. So in short, it says every integer or every positive integer is less than some other integer. Okay, or if you want, every positive integer has some integer bigger than it. Okay, so again, what does it say? Choose any integer, you find an integer y bigger than it. Choose any other integer, this is x, you can find another integer y bigger than it, and so on. No matter, this is what it says, no matter which integer you choose x, you can find y, at least one y bigger than x, the one you chose. Okay, so notice that the statement says once you choose x, you are free to choose any x you want. We can find y, there is some y which is bigger than x. Okay, and this statement is true in the integers because the integers do not stop. Okay, there are infinitely many integers. For every integer you choose, we can find some integer, some other integer bigger than the one you chose. Okay, now let's look at this. There exists an x for all y. Y is less than or equal to x. So again, let's read it from left to right. It says there is some positive integer x. So here, say these are the integers. So this is 1, 2, 3. Okay, so this says there is some integer x. So look at this domain. There is some integer x with the following property. This is the property in the red rectangle, which says that for any element in the domain, which means any integer, positive integer in our domain, you will find that this integer y is less than or equal to x. So this means if you choose any integer, so suppose we chose 1, let me choose another color. Okay, so suppose you choose 1, you will find that 1 is less than x. If you choose 2, it's less than or equal to x. If you choose 3, if you choose 1000, it will be less than or equal to x, and so on. If you choose 10 to the power 10, it will be less than or equal to x. Okay, what this statement is saying, that there is some element, some positive integer which is bigger than or equal to all integers. Okay, but this is false because x plus 1 is an integer and x plus 1 is not less than or equal to x. Okay, and again, I don't care whether this statement is true or false. I care what the meaning of it. What is it saying? So this one, it says there is some integer which is such that if you choose any integer y, you will find that y is less than or equal to x. So in other words, it says there is a maximum positive integer. This is what it says. It says there is an x which is bigger than or equal to all y, to all integers. Okay, but this is false in the integers. However, if our domain is the set 1, 2, 3, 4, and 5, and 6, so suppose this is our domain, then this statement is true, because yes, there is an x in our domain which is bigger than or equal than all others, which is 6 in this case. So this element has the property that if you choose any element in the domain, choose 3 for example, 3 is less than or equal to 6. Choose 6, it's less than or equal to itself. Choose 4, it's less than or equal to 6, and so on. So in this domain, there exists an x for all y is less than or equal to x is true. Okay, what is this x? It is the 6. Okay, let's have another example, which is okay. So here, for all x, there exists a y with the following property: p of y, where here p of y is the predicate which says y is prime. Okay, so this says, let me write it, y is prime. So we have a predicate called p of y. It's the sentence y is prime. Okay, let me continue. And x is less than y. Okay, so let's study this sentence. So what again, the universe is the set of all positive integers. So it says that for all x, so choose any element in our domain, so choose any positive integer, it has this property. Okay, in the red rectangle. And what is this property? So suppose, say this is the line of integers. The first positive integer is 1, 2, and so on. So it says for any x, so choose any positive integer you want. Say we chose this one, say it's x. Then it has this property. It has the property in the red rectangle, which says there is some y such that this y has two properties. So here you have a conjunction. First, y is bigger than x, so y should be here. And second, p of y, second y is prime. Okay, and this holds for any x. So if you choose another x, say x prime, you must find y prime in the integers which is bigger than x prime and is also prime. So in other words, this statement is saying that any integer, any positive integer is less than some prime number. Some prime number. Or if you want, you can say it in other words that choose for any positive integer you choose, we can find a prime number bigger than it. Okay, this means that the prime numbers keep growing bigger and bigger. So if you choose say 10, there is a prime bigger than 10, which is 13. If you choose 20, there is a prime bigger than 20, which is 23. If you choose 100, there is a prime bigger than 100, which is 101, say. Okay, and so on. No matter which number you choose, you can find a prime number bigger than it. Okay, this is what this statement is saying.